Hi, I'm Eric Kai, the chemical statistician, and today I'm going to talk to you about some important but subtle points about the central limit theorem, points that are not commonly emphasized enough in introductory statistics classes. In an earlier video, I described the intuition of the central limit theorem by rolling two dice. So if you haven't watched that video yet, I encourage you to do that first. I want to start by applying the CLT to the example of rolling dice. So to do that, we need to establish the expected value and variance from the parent distribution. So let's start with the probability mass function of the face value of one die. We have six values in the support set, 1, 2, 3, 4, 5, 6, and the probability of the face value taking on any one of these six values is 1 over 6. So it's a uniform multinomial distribution with 6 categories. If you apply the definition of the expected value, you'll find that mu is equal to 3.5. If you apply the formula for the variance, e of x squared minus e of x all squared, then you'll find that sigma squared is equal to 35 over 12. Do these calculations on your own if you don't know where they come from. Now, the central limit theorem says that if you have n random variables, x1 to xn, that are independent and identically distributed, and if n, the sample size, is sufficiently large, then the sample mean has an approximately normal distribution with expected value mu and variance sigma squared over n. Applying this to our example of rolling n dice, their average face value will have an approximately normal distribution with expected value 3.5, which comes directly from over there, and variance 35 over 12n. So it's not 35 over 12, it's 35 over 12n. A common mistake that many students make about the central limit theorem is by saying this. If n is sufficiently large, then the distribution of your original random variables x1 to xn is approximately normal. That statement is wrong. That is not true, because the central limit theorem says that the sample mean has an approximately normal distribution. The original random variables retain their parent distribution. So, for example, thinking about rolling n dice, the distribution of the individual die does not change just because the sample size is getting bigger. If you're rolling 1,000 dice, an individual die is still going to have a uniform multinomial distribution with 6 categories. It's not going to magically suddenly turn into a normal distribution. So it's the sample mean that gets the magic. The original random variables don't get the magic. They still have their original parent distribution. Okay? Now, there are a few more subtle points that I want you to take away about the central limit theorem. Number 1. The variance of the sample mean is smaller than the variance of one of the original random variables. In other words, the variance of the sample mean is smaller than the variance in your parent distribution. Mathematically, we can see that because sigma squared over n is smaller than sigma squared for any n bigger than 1. And of course, no sample mean is practically meaningful unless you have a sample size of at least 2. So, practically, sigma squared over n is bigger than sigma squared. But you can also think of it from an intuitive level. The sample mean is a way to extract a signal from your data. You may argue whether or not the sample mean is the best way to do so. Maybe the sample median is better. Maybe the sample mode is better. And that's a reasonable debate that we can have at another time. However, nonetheless, the sample mean is still the most widely used statistic to summarize your data to extract a signal. Now, if you're extracting your signal from multiple data, then you're more confident about where the signal is than just from one datum. If you're relying on one datum to extract a signal, then you're not as confident as relying on multiple data to extract the signal. And if you're more confident, then you're less variant. You're not going to jump around multiple values while you're trying to extract your signal. So in this case, being more precise is a good thing. Being less variant is a good thing. So that's the nice thing that the sample mean does for us. is that it extracts the signal while canceling out the noise. Another point about the variance of the sample mean is that it decreases as the sample size increases. So sigma squared over n gets smaller as n gets bigger. We can see that mathematically, but we can also think about that intuitively. Think back to my last video when I was plotting the PMF of the average face value of 2 dice. And I asked, what would happen if I'm rolling more dice? What would happen to the shape of that PDF? Actually, the shape of that PMF. Well, that shape is going to get skinnier and taller. And that's because the proportion of the extreme values is going to get lower, and the proportion of the middle values is going to get higher. The middle values are bunching closer and closer towards the middle. And the middle, of course, is the sample mean, or the average. So if you're bunching closer and closer to the middle, then you're less variant. And so that's an intuitive way to think about why the variance of the sample mean decreases as the sample size increases. Lastly, many students ask, how big does the sample size have to be for the central limit theorem to kick in and be valid? Well, it depends on what book you're reading. Some textbooks say 25, some textbooks say 30, some textbooks say 40. I think that 40 is a good sample size. However, there are 2 intuitive subtle points about this critical sample size that I want you to take away. Number 1, if you have a skewed distribution as opposed to a symmetric distribution, then you're going to need a bigger sample size for the CLT to kick in. Now, why is that? Because you are starting out with more extreme values than middle values. So it's going to take a bigger sample size for your average to show a lower proportion of extreme values and a higher proportion of the middle values. It all has to do with the fact that you're starting out with more extreme values in the first place. That's okay. You're still going to get to a normal looking distribution for your average. You're just going to need a bigger sample size to get there. Now, if you have a parent distribution with many outliers, you're also going to need a bigger sample size for the CLT to kick in. And it's the same rationale. You're starting out with more extreme values because you got more outliers. So you're going to need a bigger sample size for the proportion of the extreme values to go down and the proportion of the middle values to go up. So what's the difference between a skewed distribution and a distribution with many outliers? Well, you could be a symmetric distribution, but with very fat tails. So you're not skewed, you're symmetric, but you have many outliers because you got many extreme values. So you're going to need a bigger sample size for the central limit theorem to kick in. Okay, so I just talked about some very important but subtle points about the central limit theorem, and I hope that you will think about them, digest them, and understand the intuition behind them. As always, I encourage you to visit my blog, The Chemical Statistician, to get your short lessons and in-depth tutorials about statistics, machine learning, chemistry, and math. And I also encourage you to follow me on Twitter at ChemStatEric. Thank you for watching this video, and I hope that you learned something useful today.